We're going to talk about what this concavity word means. I want you to draw 3 different graphs, all with the derivative positive. The derivative is positive means your function is increasing, okay? So draw 3 different graphs that are increasing. Okay. And then what I want you to do at your pod is talk about, okay, you know all of the slopes are positive, but how are the slopes changing in each of those? Okay, you know the slopes are positive, but how are the slopes changing? Talk about it. So do you see how like this part of your graph is part of your graph? So talk about what's increase y is a little increase.
I know this one's
correct. We'll take care of it.
So these are not good.
Well, they're not always you were the class that we're always talking about. I don't know about color. Okay. So do you see yours right here? I want you to talk about the difference in like this.
It's just like you're passed out. It's like, what's the answer?
Okay, there's a lot of different graphs out there, but I'm going to point these 2 out specifically. The slopes are positive, yes? Because we're increasing. But let's talk about the difference between these 2. What's happening with our slopes here? The slopes are positive but getting smaller. Here the slopes are positive but getting bigger. Okay? So I'm going to introduce to you the concept of concavity. These 2 have different concavity. All right? One of them is like facing down. The curve's like facing down. One of them, the curve is facing up. Okay? So we're going to call these concave up versus concave down. Okay? Concavity is the direction of the curvature. Okay? So if you were to put your hand on the curve, would your palm be opening down or would your palm be opening up? Okay? Would the water spill out or would it hold the water? If our slopes are getting bigger, that means we are concave up. If our slopes are getting smaller, we have that concave down. Okay. So we're going to talk a lot of conceptual knowledge first before we get into any of the like the algebra type stuff and analyzing things. Okay, But I need you to understand what it looks like. Concave up versus concave down. Okay? So if we talk about a cubic function, okay, the first half of our cubic function is concave down. The second half of our cubic function is concave up. Okay? Okay. When we talk about a derivative, we describe it as what? Slope of the tangent line, or instantaneous rate of change. So if we're talking about the derivative of the derivative, we are talking about the rate of change of the rate of change. Okay, so let's interpret that. We're talking about the rate of change of the slope, right? So if we're talking about the second derivative, the rate of change of the slope, how are the slopes changing? Okay, so that's why I kind of had you describe our slopes are getting bigger, our slopes are getting smaller. That is you talking about the second derivative. How are the slopes changing? Okay. So if you want to like make a little note to yourself that F double prime means how are the slopes changing, that might be a good idea. Okay. So here when we're looking at concave up, like here I just have a parabola, okay? As we look at each of these slopes are negative, right? But as we get less steep with our negative slopes, those numbers are getting bigger. Do you agree? Like if we go from -4 to -2 to -1 to -1/2, those numbers are getting bigger. And then as we turn the corner here, these slopes are getting steeper and they're positive numbers, so those numbers are getting bigger. Okay? If we think about our slopes here with our concave down picture, okay, over here on the positive side, as we get less steep with positive slopes, those numbers, those slopes are getting smaller. And then as we turn the corner, okay, these slopes are getting steeper but in the negative direction, which means those numbers are getting smaller because they're negative. And so you're going more in the negative direction, okay? Ooh, let's go ahead and do this. Okay, so this is what we need to know. Oh, that changed colors. I don't know how I do that. Like, sometimes that happens. I have no idea how that happens. If our derivative of the derivative, so if our second derivative is positive, that means we are concave up. The rate of change or the rate of change is positive. We have our slopes are changing in the positive direction. We have concave up. Okay, it means our slopes are increasing. Okay, and I would also write that. I would write concave up, and I would write slopes are increasing. Because there will come a time where you have to look at a derivative graph and tell me information about the second derivative. If our second derivative is negative, that means our function is concave down, and that means our derivative or our slopes are decreasing. And if it's 0, we have no concavity, which will be something we look at. Okay, so yesterday I really made it a big deal where we switched from like increasing to decreasing or decreasing to increasing, right? Okay. And we put names on that. We're also going to make a big deal about where our function switches concavity. Okay. So the first thing I want you to know is that an inflection point is where we change concavity. Okay. So here is an inflection point. It's where the concavity changes. Okay. Inflection points occur when the second derivative is 0 or undefined, or they could occur. Okay. They're not guaranteed to occur there, but kind of like a critical point. That's where we have to test for it. So you know the example that I drew up here? X cubed. Okay. X cubed has a point of inflection or an inflection point. You'll hear it called either one, inflection point of inflection, at x equals 0 if we're talking about the parent function, because we change concavity there. So I'm going to put some pictures of some possibilities as far as whether we have inflection points or not, okay? Kind of like we did yesterday, where we took our critical points and tested to see if they were minimums or maximums. Just because it's a critical point doesn't mean you're going to have a minimum or maximum. No, you could not, like x cubed, right? X cubed has a critical point, but it did not turn out to be a minimum or maximum, okay? Same thing, we could have places where our second derivative is 0 or undefined, but that doesn't mean it's going to be a point of inflection. All right, so like we did yesterday, we're going to have to test for it, okay? So like here, our second derivative is 0, and our concavity changes, so we have a point of inflection, okay? Here, our second derivative is undefined. We go from concave up to concave down. We have a point of inflection, okay? However, here, our second derivative is undefined at P, but do you notice how the concavity stays the same? We would not call that a point of inflection because the concavity stays the same to the left as to the right, okay? Same thing over here. We have an undefined, and an asymptote is never going to be a point of inflection, right? Because it's not a point. But I want you to notice that we don't have, even though we change concavity here, this is concave down, this is concave up, an asymptote can't be a point, and so we're not going to have a point of inflection at that point. All right. So I want to first look at just the algebra side of things before we get into like the graphical side of things, okay? So we're going to start pretty simple. We're going to start with a polynomial. That's always a nice place to start, right? Okay, so write this down. If we are going to look at concavity, you need to associate concavity with what? The second derivative. You see the word concavity, you think to yourself, I need the second derivative. Okay? So, well, first we need the first derivative, right? What's our first derivative? Everyone together. Okay? Our second derivative would then be, okay. So, if we're going to look at concavity and points of inflection, we need to know where our second derivative is 0 or undefined. Where does that occur? We're having to think real hard about this one, right? So, like we did yesterday, I want you to make a number line, but notice how I labeled it as F double prime. Okay? You could potentially have two number lines in your work if we're talking about increasing, decreasing, and concave up, concave down. So you need to label it so you know which one is which. Okay? Our second derivative is 0 at 0. And since we're working with our second derivative number line, I'm testing values into the second derivative. So if I choose a number to the right of 0, it's going to make our second derivative positive. If I choose a number to the left of 0, it's going to make our second derivative negative. So this is what we know. Since our second derivative is negative, we know that F is concave down from negative infinity to 0. Since our second derivative is positive, we know that F is concave up from 0 to infinity. And does our concavity change? It does. So we can say that we have a point of inflection at x equals 0. And when x equals 0, we can come all the way back to our original function. When x equals 0, our y value is negative 4. Okay. So eventually, we can think about where our function's increasing, decreasing. We can think about where our function's concave up, concave down. And we can draw a graph without having to put it in our graphing calculator or really plug in very many points. Okay? Eventually we'll get to do that, but not yet. Okay? I know that one was like very simple as far as the calculus is concerned, but do you have any questions as to what we did? Okay. For it being a full moon, you guys are really, really quiet. Like all my other classes have been crazy today. So you guys are really quiet.
It's supposed to be a full moon.
It is a full moon. Did you not see it this morning?
I'm never getting invited to these things.
All you have to do is like look up in the sky.
You gotta get up early.
All right, so this is what I'm going to do because I have confidence in you. I'm going to give you a couple minutes to work on this together at your pod. I want you to take this function and use your knowledge and what we did on the last slide to figure out where this is concave up. It should not be quiet in here.
So it's 12 minus 0. Let's do.
Raise your hand if you need a little bit more time.
I know.
It's like you're coming down from.
So it's concave, or like in college sports and
Your body's adjusting. All right, our second derivative. Caleb, what do you have for our second derivative? Minus 12? X. Okay? Do you agree with Caleb's second derivative? Okay. So when you set this equal to 0, you come up with potential inflection points. Where, Dylan?
1, 0.
Okay. So then as far as the signs for your sign chart, Rebecca, what are our signs for these three intervals? So I asked you for concave up, correct? Okay. So this function is concave up. Tegan, where? Okay. And if I asked you to justify your answer, Lauren, what would you say?
because that's where it's positive on the chart.
What is positive?
The slopes of the second derivative.
Okay. So be very careful with your wording. Okay, and I know I put you on the spot there. But I did that for a reason. Okay? It's so easy to say the wrong word. Okay, when you're trying to do your justification. So I want you to be careful. What is positive? Okay, concave up you associate with positive, but make sure you tell me that the second derivative is positive. Okay? If you're going to say the word slope, we're talking about your slopes increasing. Right? The slopes are increasing. The second derivative is positive. Okay, those go in here. Okay? If I were to ask you for points of inflection, would 0 and 1 both be points of inflection? Yes, because they both have changes in concavity. Right? All right. We are going to do one more problem, but I've changed it. F of x equals x to the 2/3. We are going to look at increasing, decreasing intervals, and we are going to look at concavity. Okay? So here we go. Totally different color. First derivative. What is it? 2/3 x to the negative 1/3. Okay? Well, we like to write this as 2/3 x to the 1/3 so we can determine where the derivative is 0 or undefined. Is this derivative 0 anywhere? It is not. However, is it undefined?
Yes.
Okay, it is undefined when x equals 0. So we what?
Justified or it's decreasing and increasing.
Yes. if we're talking about the first derivative, because I want to do everything together, okay? If we're talking about the first derivative, we're talking about increasing and decreasing, right? Okay, so help me out. If I plug a number into our into the cubed root, we can have a negative in a cubed root, yeah? And what kind of number would we get? Negative. And then if we plug a positive number into a cubed root, we would get. Okay, I know it's not a cube root function, but we have a cube root and numbers, so. Okay. Let's talk about what this means. Since our first derivative is negative, we know that our function is decreasing from negative infinity to 0. And since our derivative is positive, we know our function is increasing from 0 to infinity. Okay, what else do we know? We have a minimum, okay? Our first derivative is changing from negative to positive, so we know we have a minimum. At x equals 0. More specifically, 0, 0. Okay. That was yesterday, right? Let's keep going. Now, if I want to look at concavity, we know we need the second derivative. Here's the thing. Do you want to take the derivative from this point? No, you're going to rewrite it to this anyway. It's okay to go a little backwards in your work to take the second derivative, okay? So our second derivative would be negative 2/9 x to the negative 4/3. Would you agree with that? Yes. Okay. Which is negative 2/9 x to the 4/3. Okay. And if we are looking at where the second derivative is 0 or undefined, okay, it goes very similarly to what we did with the first derivative, right? This is not going to equal 0 anywhere because our numerator is just negative 2. Our denominator is going to equal 0 at 0. Not very exciting, Mrs. Hillman, but that's okay. What? You're excited that it's 0? Okay. But be careful. This is x to the 4/3. If I plug a negative number into x to the 4/3, it's going to be a positive number, isn't it? Right? That x to the 4th power is going to force it to be positive, and then you take the cubed root of that number. And then you have the negative on the outside. So we have negative to the left. And then if we plug in a positive number, same thing's going to happen. Now, just as we talked about with our increasing and decreasing intervals, you cannot tell me that this is always concave down. You have to tell me that f is concave down from negative infinity to 0 and 0 to infinity. You have to actually break that up. Because at 0, there's no concavity. The second derivative is undefined. Is there an inflection point? No. You know what this looks like? Let's take this. So it's concave down, increasing, decreasing. All right. We need to talk real quick about a graph. Okay, and this is what we got here at 43. Man, our time went fast, didn't it?
Time flies when you're having fun doing that.
That's right. Okay, so we've worked with increasing and decreasing decreasing intervals based on our derivative, right? This graph is increasing from 1 to 6 and 8 to 9 because that's where the derivative's positive. We know that f would be decreasing where our derivative is negative. Okay, well, what about concavity? What do we need to look for in our derivative if our function is concave up? We want our slopes to be increasing, okay? So our derivative, we want it to be increasing. So we are concave up for our function from 0 to 2 because our derivative is increasing. We are concave up from 3 to 5 because our derivative is increasing. And if our derivative is increasing, that means the second derivative is positive. And then again from 7 to 9. Okay. If I'm looking for concave down, I'm looking for intervals where my function is decreasing. Derivative. If our derivative is decreasing, our second derivative is negative. Okay? We're going to work on that first thing tomorrow.